jump between the meshes. So intergrid transfer. So going first from a coarse to a fine, for instance here omega 2H to the fine grid omega H. Normally you will just use simple interpolation. You invent the points in between your coarse mesh. It's also called a prolongation. Either way you are going, from fine to coarse or the other way, you use the same operator, a large I, and it's always read from subscript to superscript. So I to H, meaning from coarse to fine. The other way it will read I sub H, super 2H, and you go the other way. So how to do this? Fairly simple, interpolation. Here we have the coarse mesh with 7 points, fine mesh with 13, and they are oriented so every other point will be at the same location. So this is the signal that you have now on the coarse mesh. Transfer the signal to a finer mesh. Okay, linear interpolation, just in the center here, in the center here, the open points here. So actually not a problem going from coarse to fine mesh. You can get a decent representation fairly easy. Linear interpolation is more than good enough. So no funny business here. And the operator, you can write it like this then. The intergrid operator from 2H to H, operating on this quantity at this grid, of course, produces now something on the fine mesh. So here, since we took every other point, yes, you can define an operator something like this for the even points and then the odd points when you take a linear interpolation, just an average. So no problem there. You can create these as a matrix operator, easier to program maybe, your choice. Not a big problem. But then we are, when we go the other way, that's where we can have some dangerous things going on. So say now you are on a fine mesh. So you have all the points here, both open and closed. They now describe that sort of a sine wave thing, more or less. And to create an image on the coarse mesh, that will mean take just every other point. That is still a good representation of the original signal. But here, if you have on the fine mesh, rather strange signal going a little up and down, something like this, down there, 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 and then pick every other point. All of a sudden you get a signal that appears smooth, and he is definitely a very, very bad representation of the original signal that you had. That was very high frequency. Meaning, if you are going to go from a fine mesh to a coarse, you must be very certain that the signal you are trying to transfer is smooth. Then you can get a good representation on the coarse mesh. If it still is high frequent, you can't do it. It's not possible to describe this high frequent noise on the fine mesh. You can't describe it on the coarse mesh. And then you have to iterate some more. You have to relax a couple of more times. In a 2D problem here, still now going from coarse to fine, from 2H to H. This will of course depend on your layout, where do you have your unknowns? Here, I think they were stored in the corners. Something like this. When you go from a coarse to fine. So this is your coarse mesh. You have all your unknowns in the corners. Of course, the corner points hit the corner points directly, no problem. But then in between here, this one, well, that's an average between these two. But the center point here, that's an average of 4. So depends on your layout. I'll show you later when I did this with the Soda algorithm for the pressure. Well, the pressure is located in the cell centers. Then it will be totally different. So it's just a matter of bookkeeping, of course, but you have to know what you're doing here. And here everything was stored in the corner, so you have some operators here that will be, some will be the direct points, some will be an average between 2, and some will be average of 4. Pure geometry, so it's not that difficult. So now going from fine to coarse, and here is where you could have some monkey business. So here you have to be careful. It's also called restriction, going from fine to coarse. The most obvious one, simple injection. You just take the points you have and you skip the one you don't use on the coarse mesh. Very simple. Yes, that would be one way to do it. Alternatively, you can use some weighting instead of just taking every other point. You can sort of create something average here, a weighting, double in the center point, but you use the neighbors as well. This will actually also be a sort of a smoother, softening down any high frequent noise as well. If you look at the figures here, here is your original signal on a fine mesh. Transfer this one onto a coarser mesh. So you see some of the points, they are injected directly. No problem there, but the question is, how do you calculate this one? If you inject, okay, then you take the value directly. If you weight them, you take all these 3 to produce a value here. And then the weight was double for him, and then 1 on the neighbors. So with the weighting, you will actually smooth the signal a lot more than if you just took every other point. So this smoothing, you can do it. Normally you just take every other point actually. But again, you have to be careful that the original signal is quite smooth. I would say the signal we have on top there, it's not that smooth. Could be dangerous. It's like when you look at an old Western movies and you see the stagecoach, 100 kilometers per hour, 1 million Indians behind it. So they have a really speed on the wheels. But all of a sudden the wheels appear to go backwards. It's the same thing here. If you're unlucky with your choice of picking your points, if the signal here is a little bit too crazy, then you can get any result down here. So you have to be sure that the signal you have up here is smooth. Then you're safe.
Check whether or not it's smooth enough, would you then normally create sort of an error check for it?
Yeah.
Maybe interpolate those points you skipped and check if they're far from the line, because here if you take those every second point starting from the first one, you would get a rather different signal than starting from the second one.
Absolutely.
So if you compare those two.
Yeah. So if you do this, then you are actually sort of solving the wrong equation on the coarse mesh, and that's a bad idea. So you have to make a proper representation of this signal down here, or else it's a waste of time. So that's important. So clearly, I would say this signal is not smooth enough. You can't do it. You have to iterate a little bit more here, get it smoother before you transfer it. But we can see some demos afterwards, see if we can see the effect of it. weighting there, yeah, you can make it however. So now we can set up this algorithm, just a two mesh system. We start on the 5 mesh. We have a solution here, or the first time you have to invent something crazy. And then you relax new 1 time. New 1, that's a number, input parameter. And of course this is the reason also why we go through this theory, because you as users of CFD programs, you will then say, use multigrid. And then the program will ask you, what cycle should I use? What is new 1? What is new 2? He will ask, and then you have to tell him. So then you have to know what you're dealing with. So new 1, that is the number of iterations on the level when we are going downwards to coarser and coarser meshes. New 2, that is the number of iterations when we go up again. So they can be different numbers. Normally they are quite small, 1 or 2, 3 maybe, not more. That's enough. But you can play around with them. Anyway, we start here, we iterate on this one to find some numerical value on the 5 mesh, which of course is wrong. Then we calculate the residual. This is the residual on the 5 mesh. Pushing it through this operator from fine to coarse mesh, producing the right hand side of the residual equation on the coarse mesh. Now we have the residual on the coarse mesh. So this is now the equation we are fighting with on the coarse mesh. And here you have to invent an initial algorithm. And of course we get 0. That's the whole point for using this residual equation. So on the fine mesh, you use the original equation. On any other mesh, on any coarser meshes, you always use the residual equation. Of course, this can be tricky when you go to mesh 3, 4, 5. Then what am I actually talking about? What quantity is this? How does he look? You can't really tell. And what is he? What's his dimensions? You can't really put any physics into it anymore. I mean, it will be the adder of the adder of the adder of the original residual. Forget it. So that's tricky. But don't worry about it. We are just solving it. Here on a 2 mesh system, we actually have to solve it on the coarse mesh. So not just iterate, but actually find a solution to this equation if you want to do this properly. Finding a solution here. Of course, finding a solution here is much more cheaper than finding it up here on the fine mesh. When you have the solution, then you go back. You take your adder, which you just have found. Remember the definition of the adder. That was the difference between you and me. So you use the adder on the coarse mesh, pushing it through this operator, now from coarse to fine mesh, and then you adjust the solution you had on the fine mesh, getting hopefully a better one. And then you do new 2 iterations on the fine mesh again. And then you can do this many times, as many times as you like. So that's just a 2-level multigrid for you. Yeah, and as he says, these news, new 1, new 2, often just 1, 2, or 3. Yeah, he's done some testing here. We can have a look at that one, but I think it's better to take a MATLAB demo here. It's the same equation, one-dimensional Laplace actually, double derivative equal to 0. So you just construct an initial field, then you know everything here is adult. The correct solution, that's 0. And here I created an initial field consisting on low frequent mode and superimposed with high frequent modes as well. So this is the initial field. now let's start. I iterate 3 times, 3 sweeps, and then I get rid of some of the high frequent noise. Then I calculate my residual, do something like this. The scale, well, nothing to worry about, since now it's quite rapid into something that's pure numerics, nothing physical. Question is, of course, when we now transfer this residual down to a coarser mesh, we sort of restrict it. So now I only have half the amount of points that I had up here. Is it the same image? Is it the same behavior? Reasonable, isn't it? Not so bad. But I would still say, question mark, maybe you should have iterated a little longer here, at least the first time. But still, it's a fairly decent representation, I think. Now, on this level, I now have the right-hand side of the equation. And here I solve it. And since it's a one-dimensional problem, I solve it using here the Thomas algorithm. So this is the solution of the equation system on the coarse level. And I've solved it to machine accuracy, no problem there. And now if you look at the solution here, this is the adder. It's just the exact opposite. So now we are going to take the adder and adjust the original signal up here. And doing that, we find this one. That was just one recycle, let's say. Just one coarse mesh correction, and you go from the blue to the red one. But the price here, of course, you have solved it on this level. Exactly. Correct. Very correct. So of course this one is quite efficient as a multi-grid. And then we zoom in. Now I have this initial field or original field, fine mesh solution. And look at the scale, it's getting quite small. It was 1, but now it's not many percent left. And now we do the same. Iterate 3 times. Feel after 3 sweeps or 3 relaxations. Really get rid of all the noise, no problem. And now calculating the residual. Okay, again move down the residual to the coarse mesh. And yes, fairly decent representation. And now again solve the system. So here is the solution perfectly on this level. Again you see, yeah, this looks not so stupid. I have some high wavy motion here, which then obviously is not going to be perfect up here. And the reason here, of course, is that this small wavy motion we have here is not perfectly represented down here. It can't be, but he does a fairly decent job. So you see the effect. You are left with sort of this wavy motion like this. Now we are on the second recycle. My fine solution here, after having corrected the alloy on the coarse mesh. And then we do 3 iterations. That didn't change much. So this actually appears sort of, well, not low frequency, say medium frequency. Anyhow, get a residual, transfer it down, looks okay, and then finding the correct solution and adjust back. And so you can continue all the way down to machine accuracy. And here he says a total amount of work units was 28. And that means 28 iterations on the finest mesh. That's the amount of work he has been doing to find the solution. And he did here, I would say, a fairly decent job. Now, if we let's see, where is it? New 1 and new 2 here was 3. If I now reduce them to 1, let's see. That was the initial field, and then just 1 iteration. And now it's a question, 1 iteration, that's don't really get rid of all the noise. Now it's a question, will I get a proper representation of the coarse mesh? That's a question, I would say. Let's see how well he performs. Finding the correct solution on the coarse mesh and see how he adjusts. I didn't do that bad. But, I mean, they are not identical. So, it is a danger there. But here it was okay. Mostly also here because you actually solve it on the coarse mesh directly, so it's fairly decent. Now this one can be more tricky. Let's see. Yeah, here we see we come into problems. Just 1 iteration here is not enough to get rid of all this noise, and this noise can't really be represented. But this is not going to be a good correction. Actually it got worse. So just 1 iteration on the way down, not good enough here. That one was better. No, not so good. So 1 iteration, definitely too little for this problem. Yeah, sort of done the same here, but yeah, it's roughly the same initial field constructed here with medium frequent and high frequent modes, and then starting using here 1 relaxation. You see you get rid of most of these crazy spikes and you get 1 smooth behavior. And then we have to switch part 2. Doing 3 iterations, you get even this noise even reduced a little bit more. But now, from now on, nothing much is going to happen. So continuing here to make more and more iterations, that would be a bad idea, inefficient. So instead, transfer to the coarse grid, and here used full weighting. And then on the coarse mesh, only 1 relaxation sweep, 1 iteration on the coarse mesh, and then superimpose back onto the previous solution. And then we are down here, getting closer and closer and closer to 0. And if we had 3 iterations on the coarse mesh, that would be even better. And you are all the way down here, very close to 0. So here, he doesn't solve it on the coarse mesh, you just iterate a couple of times there as well. That's a choice. It's also possible. So, of course now we continue this philosophy because, as you saw from the demo, the coarse mesh was solved exactly using the Thomas algorithm, meaning a direct method. So you should solve it on the coarse mesh. How should you solve it? Well, of course, since you are inside a multigrid, you solve it on the coarse mesh by using multigrids, hence even coarser mesh. So then you use as many meshes as actually you can. Of course, this will be a problem if you have Let's start easy here. You have a backward facing step problem. Sending something in here, and then you should get one nice vortex here, and then you have the outlet here. Solve this problem using the grid. Okay. Then you actually have to split up your area, something like this. And okay, the coarsest mesh you can have here would then be 3 cells. That's the coarsest mesh you can have. And then you can subdivide them and subdivide them into finer and finer mesh as long as you want, all the way down to the finest mesh. So that would be one way to easily construct your geometry, starting with the coarsest possible mesh and then just divide and divide and divide. Normally people use a factor of 2. Nobody has said that is gospel. You can actually use any dividing number. I know the square root of 2 has been tried. Of course, to double the cell size or half the cell size is much easier. So a factor of 2 is very, very common. Yes, here is a notation problem. When we now using multigrid all the way down to a coarsest possible mesh. So it was on the finest mesh you had the original equation. That was A, U and F. But on any sub meshes, any coarser meshes, it was the residual equation. So here it should read A anode equals residual. But people have agreed, I think it's just to confuse the students as much as possible, to use the same notation on all levels. So just be aware, it looks like the same equation, just with the 2 H's, but it's not. Here it is the residual equation. So I don't know why they have done it, but never mind. Just remember, here, residual equation. So now you have the recipe for a V-cycle, as we call it. You zoom down onto the coarsest mesh and then zoom up again. Starting here, new 1 iterations. We had the initial guess VH, and then we find the residual on the fine mesh, which is now going to be the new right-hand side on the coarse mesh, using this intergrid transfer from fine to coarse. So this is the residual now from the fine mesh. Here it was the anode, and we guess 0. Initial guess 0 for the anode. And then we iterate a couple of times on this equation, and then we go down to even coarser mesh. And so we continue all the way down until you are on the coarsest mesh. Here is just called LH. And there you have to solve it. Somewhere along the line here you have to solve the equation. Of course you do it on the coarsest mesh. So here you need an exact solution. And if you're lucky, when you have your fine mesh, if you choose 11 points or 101 points, you can't divide him in anything. So of course you use 64 points or 256 points. Then you can zoom all the way down till you have one single mesh point, one single grid point. And then you can easily find the solution directly, no problem, on the coarsest mesh. And then we are going to go up again. Now, what about storage? What do you have to remember? What do you have to store in your computer on the way down and on the way up again? Of course, on the fine mesh, you need all your unknowns. And this A matrix, never stored, it's just coefficients. And the right-hand side, maybe you have to store it, or maybe you can calculate it when you need it. Shouldn't be a problem. But what about on this level? Well, you have to need storage for both the right-hand side and the unknown as well. And that you have to keep on every level, because We are now going to nest our way up again. We have now the solution here from this equation as actually the anode on this level. You transfer it to a more finer mesh and adjust the solution you had and getting a better one. And then we do a couple of iterations on this level with the original right hand side that we had. So you have to remember both left and right hand side of your equation system on every level. And so you can nest your way up again, all the way up until you are on the finest mesh. So that is a V cycle for you. And normally they draw it like this on the different grid levels. And now you can start playing around with V cycle, W cycle, any cycle. And here, if you give this task to a mathematician, to a numeric guy, he will go totally berserk, because he will typically ask, when you are standing here in this algorithm somewhere, how to calculate the optimum choice? What should you do? Should you do another iteration here? Should you go down to a coarser mesh? Should you go to a finer mesh? Maybe even you can jump over one mesh directly. So finding the sort of the optimum way to do this, oh, he will love it. And he will spend much more CPU finding this optimum path than actually solving the problem. So don't talk too much about this to any numerical guy. They will just waste time and having a lot of fun, of course. But on the bottom here you have a full multi-grid V cycle. That's sort of the initial field which you then are missing. So instead of trying to find an initial field here on the fine mesh, you start on the coarsest mesh. And then you can sort of nest your way up like this. And from here on you will have then full normal V cycles. So that would be the normal way. Yep.
For the last one, then you would, I mean, you solve the real equation on the courses, right? And
You
then
have
you
to,
have
yes.
residuals.
Yeah, that's true. Then you can't use residuals down here when you first make this initial way up. Then you actually have to use the original equation, or else it doesn't make sense. You can't really put physics into this residual equation of the residual of the residual. That will be impossible. So here you use the original equation all the way.
The whole way.
Yeah.
So you would never go to residual.
But yes, you will when you have reached this point, the first time. And from here on, you can use residual equations on the coarse mesh level. Okay. Not initially. Well, maybe you can, I'm not sure, but then I think you have a very strange problem.
Because then, in order to get backs, right, then you would need to extrapolate, or like you need to transfer the initial one to the finest mesh.
Yeah, somehow. And I'm not sure how it's done. I've never done this. Normally, I always start on the fine mesh and jump directly into a V cycle. Okay, basically it's going to cost me a couple of more V cycles, I guess.
Could you also, would it be quite similar if you would start on the finest, and then instead of going step by step, you just jump directly all the way down to the coarsest, and then you go with the full cycle up? Because then you have the original.
It will actually not make any sense, because you can't represent any residual you have here on the coarse mesh in one jump. Then you have to go all the way anyway. So you begin normally with a simple V cycle. Much easier. Another demo. Starting here with an initial field, a little bit random, a little bit noisy. So now we do some iterations. 3. Now we have a nice, smooth, low frequent solution. And the residual looks very smooth and nice, shouldn't be a problem to transfer that one down here. Absolutely, they look quite similar, so this looks very promising. And then we iterate 3 times on this level. And now I create a residual on this equation. I'm taking, after 3 iterations as well, taking that residual down to an even coarser mesh. So here I would say something fishy. I would say this signal doesn't look like this one much, does it? I think there's something wrong with the code here. Let's try. Let's try. After 3 iterations, residual going down. Yeah, that one at least looks like a good representation of the one above. And then you're down to 1 point. And 1 point you solve directly. So now we are going up again. So here we have the previous field, and now the red one is the corrected. And then we do some iterations on the way up again as well, like that. And finding the residual there as well. Not that we need it, but here, this will now represent this adjustment you have up here. So not too much adjustments here, but here a little bit up. And here, I mean, it's impossible to get any physics out of this. It's just pure numerics. The physics is on the top level only, because the 4 coarse meshes, they are only the residual equations here. After 2 sweeps, the residual there, getting quite small. Adjusted the field that we had on the second mesh, corrected, and 2 iterations, residual getting small, and now we adjust finally the original. And yes, the effect at least is there. Then there's some mistake, I think. Let's try another recycle. So now this is the original signal we have. 2 iterations, getting a smooth and nice one. Residual, a little too high frequent I think, but let's see. 3, yeah, sorry. Now it was a little smoother. Sorry, yeah, because he takes 2 on the way up again and then 3 on the way down. Hence it will be 5 on the top level. Is that the same signal? Yeah. Not so stupid. And that one also looks okay. Decent representation. Oh, not quite. I have some questions about. I have to check the code again. Well, it's not my code. It's not my mistakes. I found it on the net. Yeah. So you see the philosophy here at least. Not that good, I would say. Let's do another recycle. That was better. So I think I will put a question mark. I don't think he's not as efficient as he should be. Also, this is a very easy equation. He should perform better than that. you have here a possibility to program this one recursively, and that can be messy. We actually have gotten some source codes in Pascal. I guess none of you have even, well, you have heard of it, I guess. A very old program language, so and now it's you can hardly get a compiler for it. But it was recursive in those days, so it was interesting. And programming recursively can be tough, so they're sort of done it here, but very hard to find out what the heck is going on with a recursive program. I can assure you. So don't worry too much about it. Also a muse cycle here, recursive definition. You can have a look if you like. And here, full multigrid V-cycle, explicit, a little bit easier to understand what's going on. Starting on the coarsest mesh, nest your way up on the finest, and then continuing with ordinary V cycles. This is a little bit interesting. Remember the original problem, that was AU equals F. So if you have in a real problem, you have 1000 unknowns. Then this one is a 1000 by 1000 matrix, but you never store it. I mean, it's a boring matrix. It's just a bad matrix, mostly zeros anyway, so you never store it. But if you are going to solve this one using a direct method, you could write it like this. Then you're in trouble. The inverse matrix is going to be a fool. Even though this one only occupies, say, a percent or something of all the unknowns here, all the positions, this one is going to be full. So here with the direct method, you blow the memory of your computer very fast indeed. So direct methods, they are not possible for big problems. You don't have a computer memory enough. So especially you think in terms of three-dimensional problems, forget it. You can't use direct methods. So what about our storage need here using multigrid? Well, we have this equation system on many grid systems, and we need the storage for all our unknowns. Of course we need that, and also the right-hand side, the residuals or whatever. So we need two total fields on any grid level. But here, if you go from your finest mesh to the coarser mesh, then you need only half. Here, the small d, that's the dimension. So it's a one-dimensional problem, you only need 1/2. If it's a three-dimensional problem, you only need 1/8 of the storage. So it's very nice when it comes to memory storage. You don't need much. And in practice, in 3 dimensions, I mean, you will almost just forget about these. It's this one that counts anyway. So you don't need any additional storage, almost nothing. A little bit, but not much. So it's very cheap when it comes to storage. Very cheap. And that's something that we like for very, very big problems. So he has tested here a little bit. You can have a look for yourself with different M's and N's, how many unknowns you need, how many grid levels you need. And you can easily get up into big numbers here if you go to a 2-dimensional problem. Then it can easily be a very big number of unknowns. If you choose so and so many points, so and so many meshes, of course. Okay, I can have a look at a little bit of these demos he has prepared next week, and then also we will have a peek into Krylov methods, conjugate gradient. don't think I'll go any further today. Any questions from you? That's okay. Yeah.
This is only for linear problems, right?
Yeah, your original problem here, your discrete equation system has to be a linear one.
Yeah. So how is this used in practice in fluid dynamics? Is it for the pressure Poisson?
Yeah, exactly. You need a linear equation system. But remember, I think I've said it before, I hope I had, a parabolic equation system or a hyperbolic equation system, they can be solved sort of where you march the solution forward in time or along the characteristics. It's elliptic equations that is expensive. That's where you need CPU. That's where you need a fast solver. So elliptic problems only. So yes, typically a Poisson equation for the pressure. Yeah. So you don't take the entire Navier-Stokes and push it through multigrid. That won't be. That's no point, because most of it actually will be a parabolic problem. You update the velocities, but somewhere inside there you have to solve maybe a Poisson equation for the pressure, like we did with the Sola algorithm, or other algorithms. Then you have other versions of them doing this. I won't say it's illegal to do it, to take the entire Navier-Stokes, use multigrid on it, but it.
Could you even? That's non-linear. Could you even try?
It's yeah, you can do it. Then, of course, you can't use the residual equation. Then you will have to solve the original equation on every level. I have an example for it as a reference, so I played around with it once, and it was a little bit strange because that was a turbulent problem, so I had a DNS on the fine mesh. Then on the coarse mesh, I had to use a large eddy simulation. And if I had gone in coarser meshes, then I might have to use K epsilon. That's possible, actually, yes. But I'll come back to that example. There's a reason for it. Yeah, but yeah, that's a good question.
So it's mostly used for the elliptic subproblem.
Exactly, yeah, elliptic subproblems. Very nice description of it. Yeah. Other questions? Then we stop here.
Innan så ska vi köra det, så bara ska vi säga.